Good morning, my name is Rodrigo Wang and I'm going to present the ongoing work entitled Bridging Nanoscale and Macroscale Modeling in FactSage. This work is being done in collaboration with my colleague Javier. The work that I'm going to discuss is about the development of a new module named Crystal, which will be integrated in FactSage. The objective of the Crystal module is to bridge atomic and macroscopic scale in FactSage. With the new module, we will be able to use information from quantum mechanical and atomistic methods to accurately predict thermophysical properties with effective models. As part of FactSage, the new module is directly related to other works such as the process simulation, the development of new databases, and the thermodynamic models of solution. These works are being conducted by my colleagues and will also be presented today. Our main ambition is about the development of new materials with exceptional thermomechanical properties. This is done via the prediction of the phase assemblage under different constraints and the correlation between the structure of material and its thermophysical properties. In this context, it is known that experiments are expensive and time-consuming. Also, advanced expertise is required to carry out these experiments, and they can be potentially hazardous. To avoid the drawbacks of experiments, we can use the CALPHAD approach. The focus of this approach is the description of phase diagrams. However, this method has some limitations that are related to the lack of fundamental thermodynamic data, which is key for the prediction of multi-component phase equilibria. Moreover, it is very difficult to obtain experimental data for metastable phases. In the two figures in the middle of the slide, we find the compound snapshots of aluminium-3 lithium. We see, indicated in the red rectangle in the first figure, inaccurate values of delta H and S. This is due to the lack of experimental data. In the figure below, the red square highlights the value of the heat capacity obtained with the Kopp-Newman law. Furthermore, we see in the figure in the right side of the slide that the lack of experimental data yields a phase diagram where the metastable phase is not seen originally. When we have a new compound, we have to use the mixer in FactSage. The mixer uses the Kopp-Newman rule of mixing to predict the isobaric heat capacity. However, this method requires experimental data and performs poorly at high temperatures. To overcome these limitations, we need to obtain a very good amount of reliable data that will then be fed to CALPHAD models. Then, once these models are built, we can use them to predict thermodynamic properties of new compounds. Therefore, the problem is about the obtention of thermodynamic data from computer simulations. To get reliable thermodynamic data, we need to use sophisticated simulation methods that assess matter on different scales. The multiscale simulations provide fundamental insight into the structures and the dynamics of materials and allow the theoretical prediction of material properties. We want to bring together the two first ranks that form the base of the multiscale analysis framework into FactSage. In the first rank, we have the electronic structure of matter that is described by first principle methods such as the density functional theory. These methods are based on quantum mechanics and do not have any empirical parameters. Although they provide electronic properties with an impressive accuracy, they can only handle a few hundred atoms. In the second rank, we'll find the atomistic methods such as molecular dynamics and Monte Carlo. They describe the motion of atoms based on a classical and statistical mechanics. In contrast to first principle methods, these atomistic methods can handle hundreds of thousands of atoms in a simulation and provide fundamental detail about atomic motions as a function of time. The use of these methods allow us to gather the necessary data to be used in our research and development of new thermodynamic models. To generate the necessary data, we will create a database of crystal structures in FactSage. This has been done in collaboration with my colleague Javier. This database will be used as input in simulations using density functional theory, molecular dynamics, and Monte Carlo map. Finally, these methods provide accurate and reliable thermodynamic information that we need for the CALPHAD models. At this point, we have a feeling that the initial problem is solved, since we can obtain the thermophysical data from first principle methods and atomistic methods. However, these methods are very computational intensive and most of the time require supercomputers. This is what we want to avoid by building models that will be trained on this data, but could quickly and accurately predict materials properties using common computers. These models are being developed by my colleagues Javier, Antoine, and Ricardo, and will be integrated in FactSage. How does the crystal module fit into this? The crystal module will allow the generation of crystal structures from input files or manually with primitive and basis vectors. It will allow us to modify the structures by adding vacancies and defects and by performing substitutions. We will also be able to perform structural analysis by the calculation of neighbor list and pair analysis. Some of these features are already present in the first beta version and are given in detail in the list in the left side of the slide. The figure in the top right corner shows the supercell of the aluminium-3 lithium, and the figure below we find the neighbor list and the pair analysis of this structure. If we go back to our example with the aluminium-3 lithium and change the amount of aluminum and lithium and set the temperature to 100 degrees Celsius, we see that the metastable phase of the aluminium-3 lithium with the L12 structure is formed as a precipitate along with another phase of aluminium with the FCC structure. This is accomplished while setting the B32 phase dormant in the equilib module. This is where the crystal module comes into play. We will have access to the crystal structures of species present in the matrix by clicking on them. In the right side of the slide, we see screenshots of the crystal module where the unit and supercells of the structure are displayed. The structures could then be graphically manipulated and serve as intermediate structures to other calculations. We would also be interested in obtaining their properties and storing them in our database. The crystal module will also be easily available from the compound module in FactSage, where it will allow the manipulation of crystal structures. Our aim with respect to the crystal module is to go beyond the manipulation of crystal structures. In the future, the new module will be able to calculate the internal energy of crystal structures from interatomic potentials and evaluate the Gibbs free energy with the quasi-harmonic approximation. Moreover, reading and writing of LAMMPS and VASP files will also be supported. We conclude now saying that the crystal module will drive the correlation between the structure of a material and its thermophysical properties. New modules that avoid the time-consuming calculations of more sophisticated methods are being constructed and will be available in FactSage through the crystal module. Thank you.